Hello, my name is Caleb Findley, and I'm here presenting my research about the detection of trace quantities of silica in water. I'm going to skip over my abstract since most of the information contained in it is represented elsewhere on the poster. Instead, I'm going to begin talking about the objectives and background of our research. Firstly, diffuse reflectance is the basis of the spectrophotometer used in our research. Diffuse reflectance differs from its cousin, specular reflectance, by the nature of light being scattered in many directions upon striking it. This allows for incident light to reflect many times within the cell, and not simply travel from the light source to the light receiver as the crow flies. Additionally, why specifically silica, right? Silica is one of the regulated contaminants in ultrapure water, which is used extensively in the semiconductor manufacturing industry. In effect, our goal became to be able to measure trace quantities of silica using our diffuse reflecting cell. Now, on to how we did it. You should hopefully be able to see this labeled picture of our cell. Our cell was made out of a custom extruded PTFE, which then underwent plasma treatment to give it a hydrophilic character. You can see our 830 nanometer laser is not in line with our signal photodiode, since this is not a requirement for our setup. This effectively increases our path length, since when light strikes the surface of the PTFE, it'll scatter in many different directions and bounce from wall to wall, wall to wall, and wall to wall until it reaches our signal photodiode. Now, silica isn't really known for being a colored solute, so you may be asking how we actually measure it spectrophotometrically. Well, we use something called the molybdenum blue method. Now, the molybdenum blue method uses molybdic acid and a reducing agent, in our case, sulfite, to produce an intensely colored pigment called, well, molybdenum blue. When measuring the absorbance of this compound, we noticed that there was a absorptivity maximum at 817 nanometers, which correlated to a molar absorptivity of 24,000 per molar per centimeter, or, if you prefer, liters per mole per centimeter. And although the 830 nanometer wavelength laser that we use doesn't perfectly coincide with this absorption peak, that absorption peak being at 817 nanometers, it does still represent greater than 95% of the absorptivity of the maximum, which indicates that there should be no problem with our detection of small quantities of silica. Now, onto the data. Our first set of results comes from an experiment design where a developed 200 parts per million sample was measured, diluted, and so on and so forth. Now, two major issues come to focus with this experiment. Firstly, repeatedly exposing our developed sample to volumetric glassware was far from ideal, both in terms of silica leaching into the solution and possibly the affinity of molybdenum blue to the glassware surface. So every time we diluted it, we may have been losing what we're actually measuring. Not good. Secondly, repeatedly diluting the sample also dilutes our matrix, elevating our pH and changing what the molybdenum blue actually exists in. To remedy the problems posed by this first experiment, we designed a second experiment in which 100 milliliters of water was treated as though it were a sample, with proper proportioning of reagents. To this 112 milliliter sample was added specific quantities of a developed 5,000 ppb developed sample to represent sort of a stepping up from 0 concentration to 1, 2.5, all the way up to 150 parts per billion. Now, this specific test minimizes the problems and difficulties presented by the first test because we're diluting into a matrix which is the exact same as that which our solution is in, and contact with glassware was minimized to when we were originally creating the stock solution, which was unavoidable at that time. Now, the important takeaway of this research is that we've been able to clearly detect quantities of silica down to 1 part per billion in aqueous solution using the molybdenum blue method. I don't know if you're able to actually zoom in on this picture, but this orange line right here is our 1 part per billion sample, showcasing a clear decrease in transmission of light. Thank you for your time.